Good afternoon, sir.
Good afternoon. Good morning. Good morning. Hello and welcome. Hello and welcome to the fifth class on coordination compounds. Today is the fifth class, and I think we shall continue till we complete geometrical isomerism at least. So, some of you who cannot join in Zoom can watch this very important lecture later. Without wasting a single second, let me share my screen. And this disallow your annotation. Can you see my screen?
Yes,
Yes,
sir.
sir.
Okay.
Yes.
So just to have a little practice, what is the name of the first compound?
Diamine silver one ion.
Diamino silver one ion.
Not amino. It is a
Oh, sorry,
ligand.
diamine.
It is a ligand, not amino. Diamine. Diamine, silver, one ion. The counter ion is not given. Simply you are asked to write the name of the ion. These are all cations. Diamine, silver, one ion. Then what is the name of this?
Tetraquat dibromido titanium 4 ion.
First, you find out what is the oxidation state. X minus 2 is equal to plus 2. Water is a neutral ligand. So, X comes to be plus 4. Titanium is in the plus 4 state. So, tetra aqua dibromido or dibromo, then titanium, and the correct oxidation state is IV4. I hope you understand. Amlan, welcome. What is the next one?
Tetraamine diaqua nickel 2 ion.
Yes, because this is 0, amine, aqua, both are 0. So the net charge of the complex will be same as the charge oxidation state of the central metal. So it will be diamine, diaqua, nickel, 2 ion. What about the next?
Pentaqua chloride iron.
This is not diamine. It's not diamine. Who said it is diamine?
Tetramine.
Tetramine.
Did you say tetramine? Udit? Or diamine?
Sir, maybe I would have said diamine.
Okay.
Sorry, sir.
Anyway, to err is human, to rectify is human. Tetramine diaqua nickel 2 ion. And what about this?
Pentaqua chloride iron 3 ion.
Herum 3.
Iron 3.
Squat for 10 minutes. Iron 3. Yes. Because this is minus 1, this is x. X minus 1 is equal to plus 2. So x is equal to plus 3. So this is a cationic. So iron, English name. So pentaqua, aqua, chlorido or chloro. Then iron. Since it is cation, it is iron 3 ion. What about this?
Tetraiodide cobalt 2 ion.
Tetraiodido or tetraiodo, iodido. Now we start the complex ion being negative ion, anionic complex. So AT will come. Tell me what will be the name? Tetraiodide,
Cobaltate 2 ion.
Cobaltate.
cobaltate, what?
2.
2. Because this is +2, this is -4. Therefore, the net charge is 2 minus. And what about this one, which is very unusual? Pentacoordinate nickel is very unusual, but supposing you have a complex like this, how will you name this?
Pentacyanide.
Nickel 2 ion.
Pentacyanide or cyano nickelate, because this is a complex anion, nickelate 2. Because this is +2, this is -5. Therefore, the net charge is -3. Then coming to the next one.
Diaqua tetrachloride iron 2 ion.
Are you kidding me?
Ferret 2
Are you
ion.
kidding me? This is a negative
Yes, sir.
ion. The same mistake you committed, similar type of mistake you committed there, and the opposite mistake you are committing here. So tell me again.
Diaqua tetrachloride ferrate 2 ion.
Chlorido ferrate, because it is negative ion. So ferrate, and this is 0, this is -4. Only when iron is +2, the net charge will be -2. Ferrate 2 ion. So we have, and what is the next one? This is hydroxide.
Trihydroxide zinc.
This is unusual. It's not possible. This is 2 minus. Make it 2 minus. Zinc to become +3 is absolutely unthinkable. So what?
এটা OH3 লেখা ହେଇଛି ତ ହେଇପାରିବ
Oh, sorry. ঠিক আছে. I'm so sorry. It is OH3 achi. So this is -3 + 2. The net charge will be -1. Thank you, Mr. Krishna. So what's the name?
aqua trihydroxide zincate 2 ion.
Aqua trihydroxide. Trace hydroxide you can write, because it is a polyatomic radical. So if we become very honest, you can trace hydroxide, but trihydroxide will also fetch you full mark. Then what is the last?
Potassium hexanitro cobaltate.
No. I have not completed this. Aqua tetrahydroxide, then
Zincate 2 ion.
then
Zincate 2 ion.
Zincate 2 ion.
Zincate 2. And finally, what we commonly call potassium cobaltinitride, which is a yellow precipitate. For the test for cobalt 2+, we shall be doing vigorously the analytical chemistry. And also for the potassium ion, the confirmatory test is this yellow precipitate. What is the IUPAC name of this yellow precipitate?
Potassium
hexanitrito
and
cobaltate 3.
Hexanitrito
N cobaltate 3.
hexanitrito N or simply hexanitro. Hexanitrito N, you have to write N. Cobaltate
3.
Triple I.
Because nitrite is -1, so total is -6. So this positive ion is +3. So cobalt is also should be +3, so that the charge will be balanced. It is a complete molecule, not an ion. So with this much of revision, I would like to ask you to tell me what is how these two are related. No, sir. How these two are related? What kind of isomers are these?
They both are coordination pair isomerism.
Or
Coordination pair isomer. Or solvent
that
isomer or
you don't
hydrate
use
isomer.
that, you know,
Hydrate
that
isomer.
that isomerism often is not used in India. So better
Hydrate.
use hydrate isomerism, because the ions are same. So it's not ionization isomerism, but the number of water molecules outside and inside. Here is the 5 water, here is 1 water, here is 4 water, 2 water. So these are what? Hydrate isomerism, or these are hydrate isomers. And tell me, these are which isomers?
Coordination pair.
Coordination isomers.
Coordination isomer.
These are coordination isomers. And what is the name of this compound and this compound? Can you tell me in one go, in one? Tell me the first name. We are joined by Sai. Sai, you have to, you know, jump into the fray. Nobody will wait for you to ask and waste time. So many things we are supposed to learn. You know, but you have to. Yes.
Tetraamine copper 2, tetrachloride platinate 2.
Precisely. Tetraamine copper 2, tetrachloridoplatinate 2. Plus 2 minus 4. This total will be minus 2. This is plus 2. This is 0. So it's balanced. Second one.
Tetraamine platinum 2, tetrachloride cuprate 2.
Yes. Once you always acquaint yourself in writing the names, IUPAC recommended names for everything that you are doing, then you gain more and more confidence. Acha, can you tell me how these two are related? This is cobalt.
Linkage isomers.
Linkage isomer.
These are linkage isomers. Once you write CN, everybody will understand you are talking about carbon, which is the donor. And if you write NC, nitrogen is the donor. This is the name will be. Quickly tell me the name. Jump onto one another. Jump onto one another.
Aquapentacyanide, cobalt
Aqua
3 ion.
pentacyanide, cobalt
Cobaltate
3
3 ion.
Cobaltate 3 ion.
Yes, because this is minus 5. This has to be plus 3. Then only the net charge will be 2 minus. So this will be penta.
Aqua pentacyanide,
Aqua
cobaltate,
penta isocyanide
cobaltate 3 ion.
To be very honest, I mean very strict, you have to write pentakis. Pentakis isocyanide. This is pentakis cyanide. But we usually write ditritetra for oxalato, dioxalato, not bisoxalato. Only when we have a ditritetra term in a ligand like diethylene diamine, ethylene diamine, then only we write bistress. But IUPAC is very critical about putting bistress case, tetrakis, pentakis for any polyatomic ligand also. Good morning, those who are watching now from the YouTube. It's early morning. It is only 14 minutes past 5 in India. Here in the US, where I'm staying in the East Coast, it is afternoon 4:44. So I have had the afternoon cup of tea and I'm taking this class. So we have another kind of isomer that I have not told you, that is the ligand isomerism. And we have not also revised that today. We have not revised the polymerization isomerism, where the isomers are really polymers, monomer, dimer, trimer, tetramer. The empirical formula are same. And also we have not revised the other one, which is called coordination position isomers, which are only shown by nuclear complexes, by interchange of ligands. Doesn't matter. But one extra structural isomerism you can write down in your copy is ligand isomerism. If the ligands are isomers, for example, this is trimethylene diamine, the first one. Trimethylene diamine or propane 1,3-diamine, and its isomer is propane 1,2-diamine or propylene diamine. So if you use in one PN whole 2 propylene diamine, that is called PN whole 2, and the other isomer you use its the ligand's isomer TN, trimethylene diamine, then these two are named as ligand isomers. If you are using isomeric ligands, then the name of the isomers of the complexes are called ligand isomers according to the name of the ligand. I mean, according to the isomer, because the ligands are isomers, therefore the name of the isomerism for the two complexes is ligand isomerism. Just write down at your leisure in your copy the 7th type of structural isomerism. But today we shall be taking off the interesting aspect of stereoisomerism, which is very much important for NET, JEE, and any other advanced level tests. As you know, what are stereoisomers that you have already learnt in organic? That the isomers have same structure, but I straightway write non-superimposable. Instead of writing their stereo relationship between the substituents are different, you can also write they have difference in their stereo relationship between substituents. Instead of writing that, I prefer to write they are non-superimposable. Why? Because the steric relationship between the groups branches are different. Therefore, they are non-superimposable. Stereoisomers are called stereoisomers. That you know. I am revising this. I am sure those who are watching in class belonging to class 11, please watch this little later. Once you understand clearly about isomerism, that is stereoisomerism, then only it will be very interesting to watch what we are going to discuss further. Of course, you can watch, no harm. You can understand, I'm sure. And you know, there are two types of stereoisomerism generally encountered. One is geometrical isomerism, where the two forms like cis and trans or any large number of structures, large number of forms, I can't say structures, large number of forms are non-superimposable because of the difference in their geometrical relationship. Out of them, some of them might be chiral, and they additionally show optical isomerism. That becomes Sone pe suhaga. I'm talking in Hindi. Then it adds to the total number of stereoisomers. But geometrical isomers is the beginning, where the geometrical relationship are different between the different groups, but they may be chiral, giving rise to its corresponding enantiomers D and L, or maybe achiral because there might be a plane of symmetry or a center of symmetry or an alternating axis of symmetry or axis of improper rotation Sn, I and sigma. That makes the molecule symmetric. And optical isomerism. In optical isomerism, the main condition of optical isomerism is molecular dissymmetry. Molecule has to be dissymmetric. Due to absence of, as you know, a plane of symmetry sigma, a center of symmetry, or an alternating axis of symmetry. One of them, absence of one of them will make the other two also absent. So these two. But as you know, the presence of Cn only n-fold axis of symmetry will make the molecule chiral, make the entity chiral. So that if it is dissymmetric, it is chiral, and it has got its mirror image form, which is non-superimposable with your original form. So if one is dextrorotatory or plus rotating the plane polarized light to the right, the other one will rotate the plane polarized light to the left, L or minus. So first we shall study geometrical isomerism in inorganic complexes, and we will see out of this which one is a chiral, which is dissymmetric and will exist as a DL pair. So extra one will be added because that geometrical isomer will exist as a DL pair. So we do not add +2 but +1 because that is remaining in two forms, D and L. So +1 pair. So we have to add up and find the total number of stereoisomers in each case very soon. So let us make a heading geometrical isomerism to start with. But no doubt I will be discussing optical together, but in an official manner we'll be doing tomorrow. But at that time you will be answering the question, my question more promptly than today. So let us start coordination number 4. And in coordination number 4, there are two geometries, A, SP square planar geometry, and tetrahedral geometry. This tetrahedral geometry does not show geometrical isomerism. Geometrical isomerism, let us write GI. Optical isomerism, OI. So the one which is tetrahedral will know which compound, which complex having coordination number 4 is TD and which is square planar SP. That time has not yet come. But supposing a complex is a coordination number 4 complex is tetrahedral in shape, it will not show any cis-trans isomerism. Rather, it will show optical isomerism if all the 4 groups are different. There is a chiral center or asymmetric center. So this will show GI. Tetrahedral geometry shows only OI under specific conditions if all the 4 ligands are different, all the 4 donors are different, then only it will be chiral and will show optical isomerism. But we are studying geometrical isomerism. So now make a heading SP complexes. Under coordination number 4, we shall write SP complexes. Then we will be doing number 1, M A2 B2 type. Oh, before that, let me tell you very important thing. Let us take small a, b, c, d, etc. are monodentate ligand. Uniformly, we shall choose small letters like a, b, c, d for any monodentate ligand. Different. A stands for one ligand, B stands for another monodentate ligand. All are monodentate ligands. While capital AA is a bidentate ligand. Capital letters are being identical donor. Like, who can tell me what is AA type? Can you give an example of AA type of bidentate ligand? Capital letters we shall be using for indicating. Yes, EN, ethylene diamine, NS2, CS2, CS2, NS2. This is symmetrical. So this is one of the examples. The other is carbonato or oxalato, OX2 minus. Similarly, AB we shall write for bidentate ligand with different donors. Tell me. Tell me an example. Tell me an example. Yes, glycinato. One is NS2, the other one is CO minus. Right? This is glycinato. One is the neutral head nitrogen, the other one is an anionic head, so glycinato is -1. Right? So, and the other example of this AA can be ACAC1 -1, acetonato -1. The other one example of AB is BAC. What is BAC?
Benzyl acetonato.
Benzyl is acetyl, benzoyl acetonato, BAC. B stands for benzoyl acetonato. That is because one side is phenyl group, benzene ring is there, the other side is CH3. So the two, even if they're same O donors, but they are not to be treated as identical donors. AA type is symmetrical. The molecule is, the species is symmetrical. In ACAC, this side methyl and that side methyl. So there is a resonance here acting. Therefore, the two heads are to be taken as identical. So, and remember, capital letters A, B, C, D will be using for polydentate ligands. Supposing we shall be using AAA. So this is a tridentate ligand having identical donor atom like ethylene, diethylene triamine, NS2, NH, NS2. All the, it is a symmetrical molecule. Of course, the middle one is secondary amine. The terminal ones are primary amine. So some people write ABA because primary amine is not same as secondary amine. So we can also write to ABA like di-EN. So what I intend to tell you that for polydentate ligand starting from bidentate, tridentate, tetradentate, you use the capital letters. Minimum 2 letters are to be written together to start from bidentate ligand, and many more can be grouped together for polydentate, tridentate, tetradentate, and so on. So let us start now. SP complexes once again. What is SP? What is SP? Pulak, what is SP? Superintendent of Police. What is SP complex? Good morning. What? Siddhi, what is? Yes, square planar complex. So always it is important to list out which type of square planar complexes will show GI. The first one is A2B2, two different monodentate ligands, two each. So we shall draw the structure. This is a square. These are the actual covalent bonds, dative bonds. We shall not use arrow mark since we are showing the geometry, the shape. Let us not use the arrow mark, simply lines. And if AA remaining on the same side, BB remaining on the same side, then it is called cis isomer. And if they remain in the opposite side, metal is at the center, the AA remains opposite side, BB remains opposite side. This is trans. So such type of complexes exist as two geometrical isomers, cis and trans. For example, CO NH3 to Cl2. Somebody will ask you, this complex ion exists in how many isomers? When you say isomers, it will definitely mean geometrical isomers. When you say geometrical isomers, if the coordination number is 4, 2 plus 2, 4, then definitely you have to know that it is a square planar complex. That idea you will have when you make a journey with me. You will know which one is square planar, which one is tetrahedral. For example, to be more specific, to avoid controversy, supposing I put it a nickel here and it's a neutral complex, for example, and it's a square planar complex, for example. So in that case, how many isomers it will have? This is A2B2 type. A supposing is ammonia and B is chloride ion, A2B2 type. That will show cis trans isomerism. If one in ammonia same side, chloride same side, that is cis. Ammonia opposite side, chloride opposite side, that is trans. So it exists as cis trans, two isomers. Remember the number, that is very important. Then 2 A2BC type. Simply instead of B2, I took another third type of ligand which is different from B. So same 2. You cannot have the third one. You can try. You cannot have a third one. You know, you can keep AA on the close to each other. In the last diagram, we took AA here, but that doesn't mean that every time we'll be keeping AA here. These two positions are also cis position, close to each other. These two. So anywhere you can take, you can play. If AA on the same side, BC also on the same side, this is cis. And if you have AA on the opposite side, BC in the opposite side, this is trans. You can generate many examples like Cu NH3 whole 2, this is supposing B, this is C, this is A2BC. So once you find the formula in your competitive tests, first you ascertain whether it is SP complex, because square planar complex only shows geometrical isomerism, not tetrahedral. That you will know. And in many questions, you will be given the SP complex will be given in the question. So if it is an SP complex is given, square planar complex, how many isomers, geometrical isomers it will show? It will show 2, cis and trans, because you have already remembered Ma2B2 cis trans, 2 geometrical isomers, and Ma2BC also similar to Ma2B2 cis trans. You cannot have any other arrangement than these two. The geometrical relationship is only these two different non-superimposable forms. You cannot get even if you try, it look like it will be different, but they will be, one of them will be superimposable with the third one that you generate. So you reject. So you must remember that A to B, C, that also has. And third one is M, A, B, C, D. All the ligands are different but monodentate. In that case, you have 3 GIs. Remember, it doesn't have a name cis and trans, but remember the 3 GIs. What? You can draw. Later on, I will show you mathematically using the Ballard's method how to generate the total number of geometrical isomers. This is a mathematical. So keep any one fixed and bring the other 3 to opposite position one at a time. Supposing you this time you keep B opposite to A and the other C, D in here, and in another keep A fixed. Anyone you can keep fixed. You can keep B fixed, A fixed, and now bring C to the other side, to the opposite of A. Then the remaining is BD. And the third one, give same A fixed and bring here B opposite, C opposite, now D opposite. Bring a BC to the other sides. So without other than 3, you cannot get any other fourth form. These are the 3 GIs. Keep one ligand fixed and keep the other ligands, the other 3 ligands on the opposite of the fixed ligand successively. Successively, you bring one at a time of the remaining 3 ligands opposite to the fixed ligand. Whether you keep A fixed or B fixed or C fixed, it is immaterial. Now, as a layman point of view, supposing you make a group AB and CD. And what are the other possibilities? A is opposite. When you are making a group, opposite. A is opposite to B, C is opposite to D. You can have A is opposite to C, B is opposite to D. And what more you have? Yes? What
M,
more?
A, B,
A
B, C.
is opposite to D, and what are left out? B is opposite to C. So, other than these 3 possibilities, you will not get any fourth possibility you don't get. Therefore, I told you keep anyone fixed. So here supposing D fixed, then you will find in this C, B opposite and A opposite. So here A fixed, B opposite, C opposite, other one will be automatic. B opposite, C opposite, D opposite. So in any way, mathematically also you cannot find a fourth possibility. Also here the trick is to keep one fixed and alternately or successively place one of the 3 ligands, other 3 ligands opposite to the fixed ligand successively and get these 3 isomers. And finally, M, A, B, 2 type, where AB is what? And one example we can give here, we can generate examples. In the notes that I will provide you, I'm not using that. I'm not referring to that, lest I will be slow. It is already 5:40. um, I have given many more practical examples. Here I will be generating examples. So if the four ligands will be different, then I can have an example, say copper, H2O, ammonia, ClBr. Is a neutral ligand. I want to keep copper +2. This is a fictitious example I am generating. Who knows? This might have been prepared. I have not seen. So what is the name of this compound? Aqua. Sorry. First is amine, aqua, bromido, chlorido, copper 2. This is a neutral complex. Yes or no? Am I wrong?
No, sir.
Okay. So here, just the example is, say for example, you have a cobalt, Gly2. Supposing it is +1. So what is the name of the compound? It should be bis glycinato. But you can use diglycinato. But very strictly it should be bis glycinato. For any polyatomic ligands, the IUPAC is telling use bis tris tetrakis pentakis. I don't know why. So this is, you can use diglycinato. Copper, how much copper? Tell me. Sorry, cobalt, how much? How much cobalt?
3.
Yes, good morning. Those who are watching from the YouTube directly and this early morning. Yes, cobalt?
3, cobalt 3.
Cobalt 3, because glycinato is -1. So total is -2. So this has to be +3 to make the net charge +1. So this also exists in as cis and trans forms. How? I'm showing you pictorially, then we can take examples. And one most important thing I forgot to tell you here, A, B, C, D, small a, small b. Here you write down bidentate ligand. The donor atoms must be cis. This is very, very important because sterically it's not possible to ethylene diamine CS2, CS2, NS2 is at the top, the other NS2 at the bottom is not possible at all, or this corner, this corner. So the two donors have to remain close to each other at a cis position. By default, you cannot make it trans. Sterically impossible, improbable. So with this in mind, we put A, B here and put A, B here. So that A same side, B same side. This is cis. And just if you switch it, keeping one same and the other you switch, this AB remains the same. This is the pictorial representation. A supposing NS2 and in between CS2 and then C double bond O, this is O minus glycinato. So this will be BA. So in this case, BB opposite and AA opposite. This is trans. Right? So this, for any bidentate ligand, you have to show the pictorial representation should be the letter, capital letter A, B for glycinato type. If it is ethylene diamine type, AA, but they should be connected by a curved arrow mark, a curved line to indicate the other intermediate moiety or part, like ethylene diamine CS2, CS2. In glycinato, CH2 only. And of course, C double bond O. And this is O minus, supposing, and this is NS2. NS2, O minus. So NS2, NS2 same side, O minus, same side. So this is cis. If you switch one of them, then this O minus opposite, NS2, NS2 also opposite. So that is trans isomer. You can give an example. I have already given you the example, glycinato. This is what diglycinato cobalt 3 already we have written that. So we
सर
have
कोऑर्डिनेशन नंबर कितने?
are you kidding me? Is a bidentate ligand. There are two bidentate ligand in it, you know, A, B, B. There are 4 donors. So coordination number is 4. And I tell you that this is a square planar complex. Until you know which one is square planar, which one is tetrahedral. Now, whatever I will be teaching you, I will be teaching you for this square planar complex. You presume whatever example I am giving, they are square planar, not tetrahedral. Are you kidding me, Krishna? Are you sleeping?
Sir,
Are you yes.
এটা monodentate ligand বলে act করেছে?
How? It's a bidentate ligand. If this sign, you are so
ନହେଲେ ତ
supposing it is
ଗୋଟେ ସହିତ ଦିଟା bond ହବା କଥା ନା m ସହିତ.
what English I can use for you. You are a mad chap. Supposing the example I gave you, cobalt 3 plus is at the middle, and here NH2, CS2, C double bond O minus. So this is, and this is NH2, CS2, C double bond O minus. So this, they lie in one plane, and this is square planar geometry. And of course, this will be sp3, this will be sp2. Forget about the other part. This part, and this is cis. And just you just switch the two donors, it will be trans. You understood? Why are you wasting our valuable
Yes,
time?
yes.
That means he wanted that the teacher should give an example. Very good. So we have completed the coordination number 4. Remember, which means MA3B, MA4, MAA whole 2. They do not show GI. They do not show. Wherever you place, you will get superimposable forms. You will not get any second non-superimposable form. So this is ethylene diamine type. So there is no cis trans. So these 3 formula, they do not show GI under sp complex. They are sp, but they do not show any geometrical isomerism. Coming to coordination number 6, octahedral complex. What is the time now? This will be going to be very, very interesting and important. Minimum, we shall be making 20 headings. And let me tell you before I forget, square planar complexes that we have studied under the coordination number 4, they are usually optically inactive, because there is a plane of the planar things. All planar molecules, even if the ligands are different, that molecular plane at the middle, that is the mirror plane, sigma plane, and that will never make it achiral. That will never make it chiral. So all the planar compounds are achiral. They do not show any optical isomerism. But under optical isomerism, we shall see there are some planar complexes in which the steric hindrance is so high, instead of really planar, it shows some puckering, some departure from planarity, and the real form becomes disymmetric, and they show optical isomerism. Those cases are extremely rare. Or if the square planar complex has a ligand, one of the ligand, monodentate ligand, is chiral, then because the ligand is chiral, it remains as DL form. So also the complex will remain in DL form, even if it is square planar. Or we shall study the exceptional case when EDTA will be used with flexidentate 4 donors, keeping 2 acetate ions free. In that case also, the complex, even if it is square planar, the entire complex will be disymmetric, will not have either sigma or I or Sn. Will make it chiral, and it will show optical isomerism. Those cases of rarity, exceptional cases of square planar geometry showing optical isomerism, we shall discuss tomorrow. But usually square planar complexes, they do not show optical activity. Coming to coordination number 6, octahedral complex. Number 1, M A4 B2, same as, or M A2 B4. That means 4 are of one type and 2 are of third type, but monodentate. Small letters are used for monodentate ligands, right? So this exhibits 2 GIs. Let me count. First, write down how many GIs, cis and trans, and then draw. Just for your sake of, you need not have to draw unless it is a subjective question. But once you draw and try to understand conceptually, you will not make any mistake to predict. These 4 are lying in one square plane, and the other one is above, one is below the square plane. This is the outline. These are the bonds, coordinate bonds. So if you write the 2, A, B, 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 B on the same side, this is 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 same side. So there are umpteen possibilities to show. Not that I will show this as on the same side, close to each other. I can show a B, B here. This is also B, B here, and all the remaining A, the remaining positions. If those which are only 2 in number, they remain close to each other, then this is cis. This is same as if you keep deliberately drawing different figures to make sure that if you keep AA here also same thing. They are close. They are at a angle of 90 degree. So they are also at angle of 90 degree. So don't be swayed that these 2 are closer and these 2 are farther away. But only when here opposite, here opposite, here opposite. So you can clearly know which one is opposite, which one is close or cis. You can know. Same. And when BB remains opposite, wherever you can write down, draw the schematic diagram of an octahedron like this as I am drawing. Then you put, supposing BB I will be keeping here. No worries. These 2 positions are opposite. These 2 positions are opposite. These 2 positions are opposite. There is no fixed position opposite. So BB opposite and other A, they will remain in other positions. This is trans, which is equal to, just drawing, and for the sake of your clear understanding, otherwise I have no intention to. So BB can be written here. This is same A. So this is same. So there are 2 isomers, cis and trans, and each one is achiral. So I'm just telling you that you can yourself know that these GIs, they are achiral, because either there is a plane of symmetry or center of symmetry or alternating axis of symmetry, and SN will not be required in our discussion. Can you tell me where is the plane of symmetry passes in the first cis diagram? The square plane, the plane passing through A, B, B, A. That plane, those ligands which are sitting on the plane, their reflection, their image will be also sitting in the same plane, same point. So you can have different atoms, but if they remain in one plane, that will be the mirror plane. But this is A, this is A. So this is achiral. That does not show any optical isomerism. So also, can you tell me where is the plane of symmetry passes? If there is no plane of symmetry, you can think of a center of symmetry. But first you try a plane of symmetry. Is there any plane of symmetry that you see here to declare that this is a chiral? It will not show any optical isomerism. Yes, Amlan? I can show you plane as well as sigma.
Sir,
Now
ମଝିରୁ
see,
ଯାଇପାରିବ
this is, yeah, no, this is a plane. This AA. This is a plane. This is another square. And this B is above and this B is below. So this plane, as I have outlined, that is a plane of symmetry A, B opposite. You can have a center of symmetry lying at the center of the metal atom, that B opposite, A opposite, A opposite. So in all consideration, this is achiral and this is also achiral. Understand? So none of them show any optical isomerism. Coming to M A4 BC. Same number of GIs, 2 cis and trans. Here, in place of B2, we shall be analyzing BC. If BC remains on the same side, then it is cis. If BC remain on the opposite side, that will be trans, which is not superimposable with this cis. And at random, we shall be drawing picture at random. BC, let us keep BC here. Who will? They are the same side. So this is cis, and this time I am not duplicating the structure, I mean the figure. And BC, let us write BC here, opposite, and AA in the other positions. Here BC on the same side, here BC in the opposite side. So that is cis and this is trans. And we can give example. This is NH3 whole 4 Cl NO2. This is A4, this is B, this is C. And here the example can be given CO NH3 whole 4 Cl2. In the examination, you will be given a particular formula of a complex, and you will be asked what kind of isomerism this complex will show and how many. For example, you get this question, how many? You will say it will show only 2 geometrical isomerism. Only 2 geometrical isomerism, cis and trans, because it is conforming to the formula MA4B2 or MA2B4, doesn't matter. One ligand 4 in number, the other ligand 2 in number, that will show cis and trans. Similar is the case with A4BC. The example is here, tetramine, chlorido, nitrito N, cobalt 3, because this is -1, this is -1, this is neutral. So this has to be 3, so that the net charge of the complex will be 3. Sorry, be +1, I'm sorry. So this name will be tetramine dichlorido cobalt 3. So that will exist in a cis and trans. 2 GIEs, then 3. M, we take A3B3. This is very interesting case. I try to introduce 2 GIs. Its actual name is FAC-MOR. FAC and MOR. FAC stands for facial. The facial that we do. The girls, they prefer to make facial for having their makeup. And sometimes we boys also do facial. I find in many spa and other salons, guys are sitting and making a facial. White things are being, the white coatings are being applied, and the guys are sleeping like this with something on the eye. Okay, facial and this meridional. What does it mean? I will tell you. Means some people call this as cis, some people call this as trans. If you, in any book, if you find cis for facial, fact. transformer, there are sir. I'm sorry, I'm using Hindi. Then you don't be critical. Some people call fact as cis and mer as trans. Now, how to define and how to draw fact mer? So first draw the outline of the tetrahedron. Then if AAA will be kept in such a position that if you join AAA, it will form a triangle. That triangular plane will not pass through the metal ion. It's not pass through the center, then that is facial. If that plane will pass through the metal ion, then it becomes meridional, mer. So here AAA and this is BBB. If you make a triangle, this triangle, this will not pass through, this is inclined. This will not pass through M. So also BBB. This triangle, these two BB are below the plane of the paper, and this A is down. So if you connect that triangular plane will not pass through the metal ion. So this is called FAC isomer, or some people call it cis. So FAC isomer I will define.
সেটা B है थोड़ा.
Yes, thanks. BBB. You're such a good guy, but a mad guy. AAABBB. So this is FAC. And mer, just by switching, you will find that the triangle will pass through. Just first draw the outline, then just make any A, B, you switch. Supposing you bring A here, B here, and other things you remain intact. Only I switched between these two. Switch. Don't take it as a bidentate ligand. I'm switching arrow mark AB. You find if you join A, don't join, that will pass through the central metal ion. This plane will be passing through because one of them is trans. So if two of them is trans, then definitely that AAA triangle will pass through the metal ion. So this is mer. So also BBB. If you draw BB, where is B? Oh, sorry. If you draw BBB, that also will pass through the central. Because two B's are trans. The moment you keep two of them out of the three, if you keep two of them trans, then automatically that plane will pass through the center, the metal atom. So this is mer. Some people call it trans. We will say fact mer. So how do you define fact? Let us write down. If the triangle formed by AAA does not pass through a central atom, then it is fact. Mer, if the triangle passes through the central atom, is mer. So this will be fact and mer. Now none of them is chiral, because either you can get a plane of symmetry or center of symmetry to declare this to be octahedral. So it exists only as two geometrical isomers, fact and mer. I am not spending time now to ask you to show me where is the plane of symmetry or center of symmetry, but you can yourself do that. This in here, the plane is vertically going below the plane of the paper upwards, so that BB this side this side, so plane is going, the plane is containing M, A and B. A and B and M are sitting on the plane, vertically going down and up. So it is a plane of symmetry to make it a chiral. How to make this a chiral? Mer. You tell me, where is the plane? This plane, as I told you, AB and BB, this is a plane, and A is up and this A is down. So that will make this molecule a chiral. Therefore, I told you, if you are a class 11 student, have a limited knowledge in isomerism, will be really difficult, but you can understand if you are really intelligent, you can understand. Or else I will be also making a public program for stereoisomerism and isomerism in organic in class 11. Stay tuned to watch the programs of class 11. So these two are chiral, so they do not show any geometrical, optical isomerism. I will take only few. It is 6 o'clock now. 6. I will take 4 minutes, 5 minutes to make another case, that is 4. That case is M A3 BC B2C. I'm sorry. Instead of MB3, A3B3, we make a third different ligand, B2C. And in this type, we can create NH3 whole 3 Cl3. Supposing you get either a anionic or a cationic or neutral, doesn't matter. If A3B3 is the complex and it is definitely coordination number 6, octahedral is the only choice, then this will have only 2 GIs, no AOIs. Fact and mer. There are sir, I'm sorry. Oh, then A3B2 type, number of GIs will be 3. 1, 2 mers. One fact, as some people call cis, and 2 mer. And we have altogether 3. All of them are chiral. Let me draw very quickly. You can draw A, A, A. That triangle is not passing through the center, and the other B2C, B, B, C. There, that triangle is also BBC triangle, BBC, British Broadcasting Corporation. That triangle is also not passing through the center. This is the only fact. But once you prepare, mer, then you will find 2 non-superimposable possibilities. Just supposing you interchange this. So A and B is interchanged and others remaining same. Then A become mer, because A passing through that plane is passing through the central metal atom. So also B and C. This is a more isomer, but this is more 1. Here you will find BB opposite. So if you make a switch between BC, keeping A as fixed, you will find another non-superimposable form, keeping the same A without disturbance. If you just switch between B and C, here you B, here C, then in this you find the here B were opposite, but here B, C are opposite. Here B was opposite, here BC is opposite, and B are close. These are too close. Don't confuse B, this is opposite, and this B, they are close. Here B are opposite. You look to the one which has got 2 in number, B2. So that B opposite, that B same side here. Forget about C. C will automatically adjust. B opposite, and here BB same side. Let us not call it BC same side, BC opposite. Call BB opposite here and BB same side. That will more 2. So none of them is chiral. Each of them has some element of symmetry to make it a chiral. Now, before I close, till now, no OI, all a chiral. But now onwards, I shall be discussing both GI as well as OI, so that it will be easier for you to make a list. I will make a huge list, a table of different types of formula, including monodentate and bidentate, tridentate, and all that. So we are going to the last one, 5. 4 was this, and this will be just MA3, and it is BCD. That will be the 4th type of ligand, BCD. You can create an example of this type: cobalt NH3 whole 3, H2O whole 2, and say Cl. You can create this. This is 3. 3. Ammonia 3 in number, aqua 2 in number, chlorido 1 in number, A3, B2, C. This will exist in 3 GIs. None of them is optically active. One fact to Mars. And A3 BCD type, 4 GIs. And one of them you will find will be a chiral, is symmetric, and exists as a DL form. So total number of stereoisomers will be 4 plus 1, 5. Okay, let me draw and wind up today's program. We are left with Amlan, and I understand this will be really, but since now how to draw there will be one fact, 3 mers. So fact is very simple: A, and then B, C, D. This is one fact. The moment you take mer, then you have so many 3 different possibilities. Supposing I switch between these two, I make this fixed, and this is A and this is C. So now A becomes mer. This is mer 1. You find that B, C, they are opposite. You bring D, C opposite, C, D. Then keeping that in see how I am drawing. Keeping that exact AAA without changing AAA, I am bringing now, this was BC opposite. I will B here, I will bring D opposite. Thus, there will be a switch between these two, CD. Then what I will do? I will get the other one. Now BD opposite, it was BC opposite. Then how to get the third one? We have to bring another one. There will be 3 mer. Tell me. Oh my God. As if you switch
Sir,
between
fact
B.
आगोटे पाई परिबे.
No.
The सर यदि हमें C और D ଭିତରେ interchange କରିବେ
now fact ତମେ ପାଇବ ଦିଟା fact ତମେ ପାଇବନି one fact and ତିନିଟା more ପାଇବନି କିନ୍ତୁ ଦେଖ ଏ B C ଭିତରେ ଯଦି interchange କରିବ then you will generate another non-superimposable form. This C, this is B. A will remain the same. Now see what have happened. CD is now opposite. Here BC was opposite. Here BD was opposite. BD opposite, CD opposite, and this is BC opposite. So that way we are getting 3 mores. More 3, more 2, more 1 I have brought, and most interestingly in fact is achiral. Only fact is achiral and exists as a DL pair. It has neither sigma nor I nor Sn, exist as two enantiomeric forms DL pair. So we have to total number of stereoisomers in this case is equal to 4 plus 1 pair, because 1 is already inside here. So total number of stereoisomers for this formula is 5. And you can have umpteen examples of these types, say cobalt, ammonia, whole 3, water, fluorido, then you can have nitrito. And put the bracket and create, supposing this is plus 3, this is plus 1. A3, B, C, D. This, if this type of complex example comes in the test, then close your eyes and write the total number of stereoisomers will be 5. 4 GI, and one of the GI is chiral, is dissymmetric, exists as two enantiomeric forms, DL pair forms. So 4 plus 1, 5. There cannot be a second fact. You can try and tell me. I am closing because there will be 20 cases of octahedral, more than that, in fact 30. But I will be discussing with geometry 20 cases. Others I will give you in a tabular form how many GIs and how many of them are dissymmetric and they will exist as a DL pair, so that I will add. Supposing there are 6 GIs, out of them 5 are chirals. So plus 5, not plus 10, because that 6 will contain 5D and the other 5 will be L. So 6 plus 5, 11 total number of stereoisomers. 6 GIs and 5 of them are chiral. So they will exist as a DL pair, so plus 5, 11. So in this, and I'll also tell you tomorrow how geometrically, I mean mathematically, you will visualize, you can reconcile that why, for example, a type, I'm not discussing today, M, A, B, C, D, E, F, this type, we'll discuss tomorrow. All the ligands are different. 6 ligands, octahedral. This will have 15 forms, GIs, and each of them is chiral. So 15 plus 15, 30. People, students, they remember, because at the most 20, if you remember, all these 20 will fetch you in the question. But I will make a super table, making 30 with tridentate same type, tridentate different type. So a tetradentate and different AB whole 3, AB whole 3 is there, AB whole 2, capital A, capital B whole 2, A2, AB whole 2, AB. So making it hexa coordinated, but different formula, we will generate the table. Here, why 15? I will give you mathematical basis, making grouping AB opposite, CD opposite, EF opposite, then keeping AB constant, then interchanging between them, getting 3 different forms, and then keeping AC constant, and then between BD, EF, I will interchange, I will get 3. Keeping sorry, AC constant 3, AB constant 3, AC constant 3, AD constant 3, and AE constant 3, AF constant 3. In this way, 5 into 3, 15 will be created. And once you draw them, you will find none of them will be having some element of symmetry to make it a chiral. Supposing we will reduce this to M, A2, B2, C2. Rather, we will write M. This is A2, B is gone, this is C2, and D is gone, this is E2. So that this 15 forms is our basis. We write B, in this B for A and D for C, F for E, and you will find there will be some cancellation, some repetition. You will cancel them out, and you will be finding that AM, A2, B2, C2, as we normally write A2, B2, C2. But here, for analysis, you have to write A2, C2, E2. But ultimately, we will write M, A2, B2, C2. This will have 5 different geometrical forms, out of which one of them is chiral. That you can know by drawing, but students, they remember. Once I tell you the table, discuss with you, revise with you, and make a table, it will be flowing like a spring, natural spring, rapidly from your mouth. So आज के लिए इतना ही. We close today's session. So I'm sure many guys will be benefited. This video and subsequent videos will be more and more interesting. And to see you tomorrow at the same time, because we will be closing on maybe 5th or 6th before puja. We'll be closing our program. However progress, whatever progress we might make by that time, that is okay. Then we will resume after puja. So we'll be doing at a stretch. Today is 2nd, today is 3rd. In your place it is 3rd. So 3rd is over, 4, 5, 6. 3 classes will be doing, and then 3 classes will be completing isomerism, stereoisomerism. Then we will be taking metal ligand bonding. One theory we shall complete, that is the simplest and easiest VBT, valence bond theory. Then we'll make a break. Then we'll be resuming after 13. Right? Bye-bye.
Thank you.
And those
Thank you,
those
sir.
will be watching in the YouTube, and if you really benefit, what I will tell now, don't be greedy to not to hit the like button, be generous to hit the like button, and as well, if you have not subscribed, subscribe to my channel. Bye bye. See ya.
Thank you, sir.
Bye bye, Miss RS, Badki and Chutki.